So my topic is from chapter 12, section 4. It deals with heat engines and the second law of thermodynamics. The first thing we're going to talk about is the second law of thermodynamics. Essentially, it says that if you have two objects at different temperatures, then the hotter object will transfer energy to the colder object and not the other way around. Alright, so according to the second law of thermodynamics, heat energy will be transferred from the stove to the ice, not from the ice to the stove. As you can see here, this is definitely true as the ice is melting, so it is gaining heat, is becoming hotter, so it's becoming water instead of ice. So now that we understand the second law of thermodynamics, we can start to talk about heat engines. Heat engines transfer heat energy into mechanical or electrical energy. The way they do that is through the cyclic process. The cyclic process has three steps. The first one being heat energy is transferred. The second one is the engine does work. And the third one is the engine expels heat energy on an object of a lower temperature. So an easy real-life example to see the cyclic process is in steam engines of trains. So in the steam engine, the workers burn coal in the boiler room as a heat source to heat up the water which is in the engine. So the water becomes steam and it travels through the engine to the pistons, and the pistons are connected to the wheel through a driving rod, and they are also inside a cylinder where they fit perfectly so that no air can escape through it. So the steam pushes the piston back and forth through the cylinder, creating sort of an oscillation so that it drives the driving rod back and forth, which then spins the wheel and makes the train move. So this is an easy example to see how heat energy that is transferred from the coal to the water then becomes mechanical energy through the wheels spinning. So just like that, a way that electrical energy could be created through that same sort of process would be if the rod that was connected to the piston on the other end was connected to a turbine. So the piston would then turn the turbine instead of turning the wheel, and that would create electrical energy. So now I'm going to show a video which explains this process very well.
Inside a steam engine, steam is produced by boiling water. The pressure of the expanding steam is used to push a piston to and fro in a hollow tube called a cylinder. The piston fits tightly inside the cylinder. The piston is attached to the piston rod. As the piston rod goes in and out, it drives another rod called the driving rod. The driving rod turns a wheel called the flywheel, which turns steadily even when the piston is at the end of its stroke and is not pushing.
Alright, so as y'all saw in that video, you saw the three steps of the cyclic process. The first one being heat energy is transferred, the coal is heated, and it transfers heat to the water so that it boils and becomes steam. The second step of the process is the engine does work, so the steam actually pushes on the piston through the cylinder and it moves it back and forth, so it's moving, it's doing work. And the third part of the cyclic process is actually after that, the steam will be released up into the air through the smokestack in the train.
That's pretty funny.
So in that little at-home lab I put together, you can see all three steps of the cyclic process. The thermal energy is transferred from the candle to the can. It heats the water turns to steam. The second step of the cyclic process is seen when work is done on the can starts spinning because the steam gets shot out in a tangential direction. And then the third step of that process is when the steam is released out into the air. The heat energy from the can is transferred out into the surrounding air around it. So in today's day and age, everything's about efficiency. It's all about the fastest, the most powerful. In heat engines, efficiency is determined by basically the work the engine does in comparison with the thermal energy that is transferred to the hot reservoir. So the work the engine does is determined by the amount of energy the engine absorbs. So if the engine absorbs 10 joules of energy from the hot reservoir, it can transfer 10 joules of work into mechanical energy. So the formula for efficiency is actually efficiency equals the energy absorbed in the hot reservoir minus the energy absorbed in the cold reservoir over the energy absorbed in the hot reservoir. So what you really want is for there to be no energy left in the cold reservoir. You want all of the heat energy transferred from the hot reservoir to the engine, because that's where you get your power. The more energy you have left in the cold reservoir, the less efficient your engine is going to be. So as I was saying earlier, you want your cold reservoir to have as little energy as possible, because that increases your overall efficiency. That means that most of the energy that you put toward the hot reservoir, it went into the engine, and the engine used almost all of that energy to do work, which is the essential goal. So in today's day and age, that's obviously not possible, because you're always going to end up with some margin for error. So you'll always end up with that waste energy. What some people are trying to do is what's called the combined cycle. So what it basically is it's a chain of heat engines where the thermal energy that is left in the cold reservoir of the first heat engine in the cycle is then transferred to the hot reservoir of the next one, and it just keeps going like that. So you're reusing the waste energy, and it's not just sitting there without doing any work. You're actually putting it towards something, and it's making your system overall more efficient. So what this does is it would save money, it would save gas, it would just be overall a better system than what is in place now. It's still in early stages of development. It's just being used in very high quality, very scientific power plants. Right now it is a very expensive process, because it takes special types of materials to actually extract that tiny bit of energy that is left in the cold reservoir back in and put it back into the hot reservoir. So as of right now, it's probably not the most efficient solution economically, but when you think about it scientifically, it could be a very big advancement in the field of science and engines. Another aspect of the heat engine that can change the efficiency of it is the heat source. So when we talk about heat source, it is in terms of British thermal units, which is roughly 1,055 joules. It's just the amount of energy that it takes to heat 1 pound of water 1 degree Fahrenheit. So actually, coal would be the most efficient heat source when you're talking about fossil fuels. It is 10,089 BTUs to do 1 kilowatt hour of work. Natural gas is 10,354 BTUs per kilowatt hour, and petroleum is 10,334 BTUs per kilowatt hour. So in review today, I talked a little bit about second law of thermodynamics. I had an example for that. Talked a little bit about heat engines, just like what they are, what they do. I put a little experiment together for y'all. I hope y'all learned something new through this video. I definitely did, and thanks y'all for watching.